We are finally ready to perform our regression. A good practice is always to start with the simplest regression we can do, that is a linear regression. In fact, we are defining a linear model and we are performing a linear regression first just to check whether the relationships between the features and the labels are going in the right direction. So we are going to define our linear model. We are going to use the Keras API in TensorFlow, and we are going to use the sequential class for layers. This allows us to define our linear model as a series of layers. The first layer we have is the normalizer, as we have defined previously. The second layer is a dense layer, so just a normal regression layer, where we have set the number of units to 1. The argument units represent the dimensionality of the regression layer. So when it is set to 1, it means that that regression layer is just a linear regression. Okay, if we run it, we can see a summary of our model, where we have a first visualization of the model we have just created. It's interesting to note the number of parameters for each layer, here and here. And we have also the total number of parameters of the model that has a strong relationship with the complexity of our model. We have 17 total parameters, of which 6 are trainable, and those are the parameters coming from the dense layer, and 11 are non-trainables, and those are the parameters coming from the normalization layer. They are non-trainable because we have already adapted the normalization layer to our datasets, and so we derived the mean and the standard deviation for each feature, and they are 2 times 5 features, so 10 overall, plus a constant, an intercept, that represents the 11th non-trainable parameters. At this point, we are ready to compile the model. Again, please remember, this is the linear model. We will do another model, a more sophisticated model, later. We are using as optimizer Adam. Adam is a very well-known and established optimizer with a learning rate of 0.1. The learning rate represents how fast the model is learning, but there is a trade-off between speed and accuracy. There always is. We use also as loss the mean absolute error. The loss is exactly what the model is trying to optimize. Okay, it's time to train the model. I have added this percentage time command just to print on screen the time needed to train the model. So we are going to fit our linear model to the train feature and the train labels using 100 epochs. The verbose is set to 0. The verbose is the argument to say that we do not want to print on screen every single epoch. And the validation split, this is very important, is 0.2, so it's 20%. So in every epoch, 20% of the data sets is used to do a validation step. We are ready to train, and we are going to run it. It takes a while. Okay, the training is over. We used 41 seconds to perform it. I'm not leveraging all my CPU power. Well, I'm not leveraging at all my CPU power because I'm on cloud, so it's a bit slower. Here I have defined a useful function to plot the value of the loss that our model is trying to optimize, against the number of epochs. Instead of commenting on every single line of code, it's more important to see the results. So on the x-axis we have the number of epochs, on the y-axis we have the mean absolute error of our option price. And as you would expect, as the number of epoch increases, the mean absolute error decreases. So the loss is reduced until a limit that is below 40. In this cell, I'm simply storing the results of the linear model for a comparison that we are going to do later. In this cell, I'm printing the coefficients of the linear regression, and as you can see, at least the signs of the coefficients are right. So we have a positive relationship, a positive correlation between the spot price and the option price. The correlation is negative with the strike price, and then positive with the remaining features of time, risk-free rate, and standard deviation. Given that this is a very simple linear model, I would consider this result already a very remarkable one. It's now time to do the real deep neural network, so not just a simple linear regression. We are going to define the model with the sequential method of the Keras API, as we did before. The first layer will be a normalization layer, so our standardization procedure. Then we have 1, 2, 3, 4, 5 layers of 64 neurons each, and with an activation function that is ReLU. In the end, the last layer will be a dense layer with just 1 neurons, and that's coming from the fact that we want a single value that is the option price. Here we are compiling the model. Our loss will be a mean absolute error. I've tried to use also other type of losses, but again, they didn't prove to be better. Our optimizer is Adam with a learning rate of 0.001. Then we build the model and we print a summary. Okay, here in the summary you can see a summary, of course, of our model. Interestingly, there are 17,100 parameters, of which again 11 are non-trainable, and the remaining are the trainable parameters. So as you can see, this time the model is much more deep, much more complicated to train. We are ready to train the model using this command here, fit. We are fitting the model to our features and our labels. Again, the validation split is 20%, and we are going to have 100 epochs. Let me run it. Okay, now it will take a while. Okay, it's done. It took 1 minute 22 seconds, so not so much. Now we plot the loss against the epoch. We have in blue the loss, the one that we are training, and in orange the validation loss. So as you can see, it started decreasing since the first epoch, and then more or less it plateaued. Okay, now I want to show you a comparison between the linear model and the deep neural network using the test data. So as you can see, the deep neural network is much better than the linear model, where we achieved a loss of 36, while in the deep neural network just 6. Okay, now that the model is trained, it's time to test and understand what the model has done. I'm not going into the code because they are just simple plots, but let me show you this. This is the graph of our predictions derived and computed by our model, our trained model, the deep neural network, against their true values. The closer is this graph to a 45-degree line, the better. So as you can see, we are not so far away. It looks promising. Okay, so if we define our error as the difference between the prediction and the label, so the true value, and we do an histogram, we can see that our errors have more or less a normal distribution, and that's good. That's good enough, because it's saying that, well, the model isn't skewed, isn't asymmetric, and it could be a good model. Now I want to define a relative error, that is the ratio between the error and the test label, that is the value of the option. If I do it, we see that there is at least one value that is close to minus infinity, because it's minus 1.2 times 10 to the power of 88. In fact, if we see some descriptive statistics, we have that for the relative error, I underline the relative error. This is not the error that we have minimized during our training. This is the relative error that I have just defined. We see that we have a mean of minus infinite. The minimum, in fact, is minus infinite. So we will need to further investigate that. So at this point, I try to remove the infinite values in the set, and then I try to plot the relative error against the call value. As you can see, the relative error is quite big when the call value is quite low. That kind of makes sense, because when you have a small absolute error and when the call value is very small, we end up having a big relative error. This behavior is maintained for higher values of the call value. So even though is much less relevant this time, but the behavior is maintained. Now let me show you the quantiles of the relative error. We are on a log scale, and here we can see that most of the set of the relative error has a very low value, while a bit at the beginning and a bit at the end are extremely high. In fact, let's focus on the quantile between 10 to 90. If we do that, we see immediately that almost 80% of our test dataset has a relative error that is below 10%. This is a very remarkable result. So to conclude, even though far from perfection, our deep neural network proved to be a good approximator of the Black Scholes model, showing some margins of improvement when the call value is quite low. Well, that was all for this video. I hope you liked it. Feel free to write some comments below, and see you to the next video.